Good morning, everyone. I am Chihaya Anon from Haneoka Girls School. Today, we will be talking about the last problem from this year's BMO 2. Let's take a look at the problem first. How many different sequences of positive integers satisfy U1 equals 1 in the following recurrence relation for all n no less than 2? It really looks a bit complicated, and the recurrence relation given is not a typical one, so why don't we analyze the conditions first? First, UN is a sequence of positive integers. Second, the first term of UN is 1. You are also given a recursive definition for UN. Now that we have a thorough understanding on what the problem is talking about, let's ask ourselves a few useful questions. First, what makes it possible or impossible for us to determine the sequence given its first term in the recursive definition? If the sequence is unique, how can we find it? If the sequence cannot be determined, we need to think about a few other things. How can we ensure that the sequences we find satisfy the conditions? As importantly, how can we assure that the sequences we find are all the sequences that satisfy the conditions? We will begin with the first question. If we reindex the given recursive formula, we can get an alternative one, which works for all n larger than or equal to 3. This is a second-order recurrence relation. Therefore, not given U2, the sequence cannot be determined. This is the same as saying that every different U2 gives a unique sequence. We will continue to answer the second question, which will seemingly lead to a decent solution. We will make a guess first. The guess comes from a few experiments with the sequence. Our conjecture states that UN is a sequence of positive integers if and only if positive integer U2 divides 3 to the power of 2025. We start with the sufficiency part. See that UN plus 1 is an integer implies that UN minus 1 is a factor of UN squared plus UN plus 1 to the power of 2025. We can now substitute UN with the given recursive formula to get the following result. This also implies this, which can be obtained by multiplying the right-hand side with UN minus the squared. We manipulate this with some basic modular arithmetic to obtain this. Specifically, when n equals 3, we can show that U2 is a factor of 3 to the power of 2025, and we have completed this part of the proof. We continue with necessity. We will use mathematical induction to prove this part of the theorem. For all integers n greater than or equal to 4, if we are given that UN and UN minus 1 are integers, then we know that UN minus 1 is a factor of this number. By construction, we can obtain an equivalent expression. We apply the Euclidean algorithm and show that UN minus 1 and UN minus 2 are coprime based on a few properties of integers. Then, we can conclude that UN minus 1 divides this expression. Due to the fact that UN is an integer, the right-hand side is apparently an integer. This implies that if our inductive hypothesis stands, UN plus 1 is an integer. Note that U3 has to be an integer by the recursive formula. Since U2 divides 3 to the power of 2025, we can show that U4, which is equal to the following expression, is an integer. This serves as a proof for the base case when n equals 4. Now we have shown that if U2 is a factor of 3 to the power of 2025, UN is a sequence of integers. We also have to ensure that the sequence consists of positive terms. For all integers n greater than or equal to 3, given that UN minus 1 and UN minus are positive, it is trivial to show that UN is positive. This is the inductive step. Note that U1 and U2 are both positive. This is the base case, and we have provided a proof for the theorem. Therefore, U2 is in the form of 3 to the power of k, where k is an integer between 0 and 2025. This means that there are 2026 sequences, giving the answer. Thanks for listening!